Hi, this is an AP Chemistry video. We're going to be covering 14.5, all about weak acids in the Zumdahl textbook. So previously to this lesson, we talked about strong acids and how we can assume that the hydrogen ion concentration when it dissociates is the same as the molarity of the acid to start with because the reactions go essentially to completion. Now we're talking about weak acids. So if I have a weak acid here, and this is HCN, it would, in water, most of it's going to actually stay together. So we can't do these problems the same as we could do a strong acid problem. The major species that are in a solution, in this case, it's going to be the hydrocyanic acid and water. And then who's producing the hydrogen ions, or, what is controlling the pH here? I would want to think about HCN will be one of the sources of hydrogen ions, and autoionization of water is the other source. The Ka for the hydrocyanic acid is 6.2, 10 to the negative 10th. For water, the Ka is the Kw at 25 degrees, which is 1.0 times 10 to the negative 14th. So because the Ka is larger than the water, we're going to assume that the hydrocyanic acid is the one that's controlling the pH here. So these are the steps that we're going to be using when we solve equilibrium acid problems, and it'll be applied similarly to bases. First thing I want to talk about is the 5% rule. The Ka values are known with an accuracy or plus or minus 5%. So sometimes it is possible to, in fact, you'll see this quite a bit, where if the Ka is small enough and the molarity of the weak acid is large enough, the difference between them, then we can kind of negate or consider that the value of X is negligible. That will make more sense in just a second. So the book covers the 5% rule. I prefer a different method, which I'm going to teach you right now. So here's just kind of an exercise. So if I said, what is the difference, subtract 5.0 10 to the negative 6 from 0.135. I think it's helpful to take this out of scientific notation. And then if I do this on my calculator, I think I have the right number of zeros. My calculator says 0.134995. Our rules in chemistry for subtraction and addition are to go to the least decimal places. So in chemistry, my answer is going to be 0.135, which is the same as my starting amount. So essentially, this is so small that it didn't matter. So that's what we're going to call the X is small approximation. How do I know when I can do it? So here's an example of someone else's rice table, and you can see that they're starting out with 2 molar HA, which in this case is acetic acid. And initially there's no hydrogen or acetate ions. And then we can assume that we're going to be making, the hydrogen and the acetate ion and using up the acid. But what I can do is, if I see this X is negligible, I can essentially take it out and only put a 2 in the denominator, which then allows me not to have to use the quadratic formula. So how do I know when I can do this? What I do is I look at how many orders of magnitude different are there between the molarity initial of the acid, so essentially this is 10 to the 0, and the Ka value, and that is 1.8 10 to the negative 5th. So you can see that these are 5 orders or powers of 10 in magnitude different. So the rule that I go with is that if you have 2 or greater orders of magnitude difference between the initial acid concentration and the Ka value, then I can assume that that X, not the others, that X is negligible. So when I do sub in then to the equilibrium expression, I can say this is negligible, and then I can just put a 2 in there. And that makes the math of this much easier. Sometimes I would probably write this, that we are assuming that the X is much, much less than the other, the molarity. So because the Ka is so small, this acid isn't really going to break up to much. It's not really, the equilibrium lies to the left. So the small amount of change that we get, that it is going to reduce down from the 2 molar that we start with, is essentially negligible. If it's similar to that problem we started in the beginning, I can subtract it if I had the number, but it's going to end up being nothing. So I'll show you this in action in quite a few examples. So here is an example of where you can look at when is the X's small approximation valid. So if you look at these combinations of the initial concentration of the acid compared to the Ka value, you should be able to pick at least one here where it's not valid. So let's look at these one at a time. I find it helpful to put them both in the same format. So I'm going to write this as 1.00 10 to the negative 1. So then I can just really compare the exponents essentially, and I can see that there is a difference there that is greater than a magnitude of 2 powers of 10. So this is a place where, yes, go ahead and say that X is small enough that we can just ignore it. Next one is even, so this would be 1 10 to the 0 compared to the negative 6. So this is also a large enough difference in magnitude that we can do the assumption. This one here, if I do write it in scientific, I get 10 to the negative 2 compared to 10 to the negative 3. These are only 1 order of magnitude or power of 10 different. So this is a case where you wouldn't want to do the approximation. You would have to use the quadratic. And then lastly, this one is 10 to the 0. And so there is 3 powers of magnitude difference between them. So I could definitely use that. So all of these except for C are times where I can say that the X is negligible and just eliminate it. So I'll show you how to do that. So here's an example of a problem that we're going to do. So this is hypochlorous acid. It's used in bleaches and swimming pools. It has a Ka of 3.5 10 to the negative 8th, and we're going to calculate the pH of a 0.100 molar solution. So first of all, the major species in the solution are going to be the hypochlorous acid and water. Which one's controlling the pH? I know it's this one because it has a Ka that is larger than the Kw of water. So we're going to ignore the contribution of hydrogen ions from the water. It's, again, negligible. So then I'm going to start the problem, and I'm going to use a rice table. So my reaction is the hypochlorous acid, and that will dissociate into, this isn't the way I normally write that ion, that's the hypochlorite ion. And then we we know our initial concentration of the hypochlorous acid is 0.1 molar. These are going to be 0. And then the change is, this is going to be used up, and these are going to be made, and they're all in a 1-to-1 mole ratio, so they're all equal to X. And then my equilibrium value is going to be 0.1 minus X, X, and X. So now I'm ready to sub into the Ka expression, which Ka is going to equal the hydrogen ion times the hypochlorite ion over the hypochlorous acid. And I can sub in. So my Ka is 3.5, 10 to the negative 8th. I'm going to, this is hydrogen ion is X, hypochlorite is also X. And then here I would have 0.1 minus X. So this is one where this is really 1.00 10 to the negative 1. You can see there's a very large difference between these. So I am going to do the X is small assumption. So that means I'm not going to use this. It's so small that it won't matter, which means I can take it out of here. And then it's a much easier problem to solve. Then it's just X squared equals 3.5 10 to the negative 8th times 0.1. And then I would just do the square root of both sides. And when I do that, by the way, when I do this, I should somewhere note that the X is much, much smaller than that beginning molarity. That's why we're able to make that assumption. So when I solve here, I do get X, which is my hydrogen ion concentration, which is 5.9 10 to the negative 5th. So in this case, I think I asked for the pH. Yep, so pH, once you know the hydrogen ion, is very simple. And you should get 2 sig figs, so you have to include those 2 after the decimal. You can verify this with the 5% rule. I'll just do it once to show you. So for the 5% rule is that your value of X compared to the initial concentration of the acid times 100 has to be less than or equal to 5%, since the 5% is the value that the Ka value could differ by. And when I do this, so I would take my X, which is my hydrogen ion, over the molarity of the hypochlorous acid times 100. And when I do that, I get a really small number. So that's just verifies that my assumption that X was small is a good one. So the next question that I have for you is when we mix together more than one weak acid. When we do this, we're going to choose the acid of the weak acids that is strongest, and then that will be the one that is controlling the pH. So when I do this question here, I'm mixing hydrocyanic acid, which is a source of hydrogen ions, and the Ka is 6.2 10 to the negative 10th. And then I'm also mixing nitrous acid, another weak acid. And this time the Ka is 4.0, 10 to the negative 4th. You can always look these up if you haven't been given them. And then we know we have the autoionization of the water. So I am going to pick this nitrous acid as my major contributor of hydrogen ions, the one that is controlling the pH. So that means the hydrogen that's coming from the hydrocyanic acid and the water are negligible. So now I'm going to do a rice table with that reaction and those beginning amounts. So my nitrous, my initial concentration is given in the question as 5. These are 0. Change minus X plus X plus X. Equilibrium 5 minus X, X, and X. Can I make the X a small assumption? Let's see. This is 5 10 to the 0 compared to 10 to the negative 4. and that is greater than 2 orders of magnitude difference, so therefore yes. So because I can do that, I'm going to ignore this x. So then I can sub into the Ka, my expression. And the Ka, remember, was given is 4.0, 10 to the negative fourth. This would be x and x. And then the concentration of the acid, again, we're kind of making that x is small assumption because we're assuming that it's the same afterwards. So when I do this, then I'm going to get x squared equals 4.0, 10 to the negative fourth, times 5.0. Then I just take the square root of both sides.